me very, very closely on various projects. He is one of the respected academics in the field of AI, quantum computing, sustainability, etc. He is also listed among the top 2% scientists as per Stanford University. I have personally attended his sessions. He has also delivered keynote address at the conference organized by the Curtin University recently. So I can assure you that this session will be very useful for all of us. So I invite all of you to make the most of this session and also to join FEDA. If you are not already a member, please join FEDA. There are many, many benefits. You have recently watched the video. So if you become a member, you can freely attend these kind of workshops, seminars, conferences, and a lot of business opportunities, while also gaining valuable network opportunities. So make use of that. So I wish you all the best. Thank you. Over to you, Sahal.
Thank you, Professor. Now, to introduce our distinguished speaker for today, I would like to call upon Ms. Maya, who is the treasurer of the FEDA Global Council. Ms. Maya, over to you.
Thank you, Mr. Sahal. So I would like to introduce Professor Balamurugan Balusamy. He is currently working as a professor and associate dean academicians in Shiv Nadar Institution of Eminence, Delhi-NCR. Stanford University has recently released an update of the list that represents the top 2% of the most cited scientists in various disciplines. He is a part of the top 2% scientists worldwide 2023 by the Stanford University in the area of data science, AI, and ML. He is also an undergraduate professor and Department of Computer Science and Information Engineering, Taylor University, Malaysia. Prior to his assignment, he was a professor in School of Computing Science and Engineering and the Director, International Relationships at the University, Greater Noida, India. His education, blockchain and data science, his academic degrees, and 12 years of an experience working as a faculty in global university like VIT University, Vellore, has made us more respected and prominent in this domain. He has 200 plus high impact factor papers in IEEE. He has done more than 200 edited and authorized books and collaborated with the eminent professors across the world from top QS ranked university. Professor Balamurugan Balusamy has served top up to the position of associate professor and stint of 15 years of an experience in VIT University, Vellore. His passion is teaching and adopts different design thinking principles while delivering his lectures. He has published 80 plus books on the various technologies and visited 15 plus countries from his technical course. He has several top-notch conferences in his resume. So he has published 200 plus quality journal conferences and book chapters combined. He was traveling more than 15 countries for his academic and research assignments and talks. So thank you once again. Over to you, sir.
Thank you, Ms. Maya, for this introduction. Ladies and gentlemen, please join me in welcoming our speaker who will now deliver their talk.
Thank you. Thank you, one and all. Can I ask whether my screen is visible and I am audible?
Yes, sir.
Okay. Thank you, Maya, for your kind words. Thank you, Dude, for your kind words. And thank you, Professor Pon, for allowing me to talk to all these people. Though I am from a different country, through your network, I'll be able to deliver the latest of technologies that is going to build the newest of businesses, not only in UAE, but across the world. Thank you, Professor Pon. So let's go to our lecture. and I'm very happy to be part of the first lecture of this series. That is something that is more respectful. Plus, maybe after 40 to 50 lectures is being done, I will be still remembered for a person to be giving this lecture as the first one. So I'm very happy to have this thing. So like when we had a discussion about what to speak, so like I was trying to speak on artificial intelligence, but still I was a little reluctant because many lectures have been taken by people. So I divide listeners as types: somebody who is very technically prone, sound, somebody who is mediocre, trying to catch up with the latest. On the other hand, somebody who are users, so they want to become an expert. But they all these three would have already got lot of information and knowledge about artificial intelligence, explainable artificial intelligence, all that stuff. But then we just zeroed it upon quantum computing. Quantum computing is also coming up. It is going to take over a lot of businesses, not only in UAE, but across the world. So, but on the other hand, it's very, very important that everybody should also know about artificial intelligence. So we came out with a topic which is quantum artificial intelligence, which is going to do lot and lot during our this generation of time. Okay, so we already know about high performance computing, which is being used for doing a lot of analysis, especially for people who are into business, marketing, and finance. Unless they have data and unless they have data driven decision making, unless they have data analytics, they will not be able to run one single day in a company, because most of the company has enormous amount of quality data which is being used to move the company forward, that everybody knows, either in order to improve the sensex of a company, or the profitability of a company, or how to do a tie-up, how to merge one company with another. A lot of things have been done by means of high performance computing. And so we integrated all this. So who are the listeners? Who are the people who will be engaged with FEDA now, possibly, or in upcoming days? So, like, we came out with an idea that let's go for an integration of quantum and HPC, that is high performance computing, for sustainable quantum AI. And especially, I'll be giving special focus on industrial digital twins, as well as I'll be talking about what kind of businesses has been enhanced by means of this kind of newer technology. That's what I'm going to speak. So let's go into the topic. Um, how many of you know about quantum? Like, can you just send me what you can say, yeah, thumbs up or something? How many of you know about quantum? Have you heard about it? Okay, good. So, um, like if you want to know about quantum, we have to go back and we have to talk something about quantum theory. Okay, quantum theory is not a new one. Good. I can see in chat a lot of people answering. Very good. During the question and answers at the end of the session, maybe after 1 hour, 45 minutes, last 15 minutes, I will dedicate for question and answers. You will be able to ask any of the questions you wish to ask, and I'll be able to answer it to a larger extent. Okay, so when you talk about quantum theory, it has been there for almost 100 years. So, and people have said that the world is not uh, linear, but it is quantum. So this is something that science have said. Okay, so everything in this world, for example, take how a leaf grows. Leaf has a pattern to grow. Am I right? So if you take a plant, if you go for the series of leaf, how it goes. So there is a theory that states that leaf takes into account a Fibonacci theory and grow. So you can see like one, then after the two, after the three. So you can see the rhythm in it. So nature has certain pattern inside it, but human being doesn't have that kind of intelligence or equipment to understand the nature. So for that, the first step what human being has done is understanding quantum theory. So thereby understanding nature. Okay, so when I talk about nature, it's not only about plants, it's all about animals also, like human animal also. So how a brain works, if we want to understand how a brain works. They have been studying brain for almost 400, 500 years, more than that. And this last 100 years, they have come out with a lot of understanding of brains, the way it brain reacts, the way the brain works. And we have a separate field called computational cognitive science or brain science only to deal with the working of brain. Okay, but still, the scientist, on the other hand, especially the doctor who turned into scientist, they have told us that we haven't understood even 2 to 3 percentage of brain working. Okay, because once we keep on understanding the way the brain reacts, way the brain works, it is going to be finding out a lot of cures, and it is going to find out a lot of medicines for especially something called like mental balance or mental health. Because in all the developing countries, and especially the developed countries, more than physical human problems, the mental human problems are rising. Because physically they are fit, they are working very hard, they are very successful, they go to gym every day, they are physically active, they are outwardly extrovert, but still when they are alone, they get into a depressed state. And you can see a lot of people getting into several other states. Okay, so if you want to understand and give them a prescription, then you need to understand the brain, not only a single brain, how typically a brain works. So which is very hard for our normal computing to do it. Okay, normal computer or computing, we have a process. It discerns certain thing to understand something. For example, if I want to know brain, I have to cut the brain and understand. If I want to know about lungs, I need to cut the lung and understand. But on the other hand, if I go for quantum computing, there can be a lot of inference that can be done, which is needed for the upcoming years to come. Okay, so you need to know about quantum theory, which is very old. After you know about quantum theory, there is something called quantum mechanics. Okay, which is a partial updation of quantum theory. On the other hand, there is a parallel field called quantum physics. Got it? Quantum theory is there, quantum physics is there, quantum computing is there. You can note it down. You can just go to Google or any of your large language model and ask these questions to understand more. And why we need to know all this is these are some technologies which are upcoming. So if you invest your time, if you invest your energy on the upcoming technologies, you will be seeing success. That's a simple thing. For example, you take us, we are been working on artificial intelligence for a long, long time. When people were not talking about artificial intelligence, somewhere around 2005, when we were working on SOAP, when we are working on XML, when we are working on web services, when we are working on inference theory, and then artificial intelligence. Okay, so but we do not know that it's going to be a big boom, like it is going to overtake a lot of things. But we do know that a lot of business decisions are being to be taken by artificial intelligence and data analytics. So, but now artificial intelligence has almost taken over the world. Similarly, like we can't say only artificial intelligence is the end, but the main thing what we are going to say is like we have multiple technologies coming up. Even there will be time when artificial intelligence will be overtaken by some other theory. Maybe it can be quantum information science or theory, but it is not something that is going to replace artificial intelligence. I am making this point very clear. It is not something that is going to replace artificial intelligence, but it is going to aid artificial intelligence to work in a better way. So far, so good. Can you understand my language, my accent? The speed is okay. Can I get a thumbs up or thumbs down? I don't mind. Okay, perfect. Good. I can get a thumbs up, a lot of thumbs up. Good. So we can keep going in the same phase so that I want you to learn at least 40 to 50 points in this 2 hour session. How many points? 40 to 50 points. That's what my interaction is all about. Okay. So quantum theory, quantum physics, quantum mechanics. All these are already there, theoretically exist. And suddenly, before 15 to 20 years, people started making quantum computing. What is quantum computing? Okay. So, for example, you take a normal computer, we make use of silicon. Am I right? Silicon is a kind of sand that we use for creating or manufacturing ICs, or we call it as integrated circuits, or we call it as chips. Okay. So now inside the chips, it has the ability to store charges. Everybody knows it. You would have studied in your high school, but still, I have to build a plot to talk about quantum. So I'm saying this. So there are possibility of charges to be stored and discharged in an IC. Okay, so we make use of this probability or this possibility of a silicon, and we used to store some data inside it, and the same data is also being transmitted across from one IC to another through cables. Maybe now we are using fiber optics, even advanced transmission technology like laser is also being used. Okay, so this is the scenario. Okay, so we have only two things to do. One is 0, another is 1. Okay, so these are the two bits we have, and larger amount of bits are called as bytes. So we do this kind of computing, and we can call it as a traditional computing as far as now. Perfect. Okay, now coming to quantum computing. Okay, so what you can do at a time, you can either have two states. It can be 0 or it can be 1. Okay, so we are completely eradicating a possibility of a state which can be between 0 and 1. There is a possibility. Imagine, take a probability example. Let's go into mathematics now. Take a probability example. I am flipping a coin. Got it? So you have a heads, you have a tail. Whatever coin, whichever country coin you flip, we always have a head or tail. So this makes a coin. Got it? So there are only two faces. So probability of getting a head 0.5, probability of getting a tail 0.5. So total probability of this event is 1. Everybody knows it. But when I flip the coin, okay, so there is a possibility, there is this many number of heads, this many number of tails, and when it lands, it can have a head or tail. Okay, so now I'm also calculating in it the pressure I'm putting it to throw the coin up, or the amount of energy I'm spending it to flip the coin, all this stuff. So is it possible for a traditional computing to compute all the state right from the point I'm taking the coin, flipping it on the ear, how many heads, how many tails, down, what is it? Not possible. So only we have something called quantum computing, where there are more than two stages or two events can happen. Got it? So I can say like there are more than zeros and one. So it can take multiple states. Okay, so that I'm completely changing the core primary logic of a probability by means of using quantum computing. Okay, got it. So how it can be possible? Because in silicon we have zeros and ones, because signal, it is a simple electrical signal. Okay, so how I'm going to store this kind of data? Okay, so good, it's a right question. So instead of silicon charges, I'm going to make use of atoms in that proton, neutron, electron, all that stuff, because they are multiple in nature. And for example, any material science matter you take. Got it? So, for example, iron ore can be a gold, it can be diamond, whatever it is, sapphire, whatever it is. So, I get into the molecule of it, I get into the finite element of it. As I already said, proton, neutron, electron, whatever it is. Imagine I'm getting into electron, and you have seen in your chemistry lab how an electron moves. Am I right? It's a lively thing. It moves. For example, if you take hot water, how the atoms are condensed or how the atoms are distributed. If you take cold water, how the atoms are being distributed. There is a difference between it. Am I right? Can you understand this? Good. So now I will take one such elements and then I'm going to store something inside it. Okay, so it can be a 0, it can be a 1, or whatever it is. Got it? Now I have got an entirely different space to store, and I have got entirely different possibilities other than zeros and one to store. Okay, so completely I'm changing the computing paradigm, which is very essential for doing a lot of computing. Okay, because the zeros and ones are not enough for me. And how it is not enough for me, I am going to say why it is not enough for me. I am going to say in this lecture. Same. Got it? So now I have got a lot of things. Okay. Silicon works in normal room temperature, but I will be able to get into an electron of an element, take gold and compute something inside it? No, not possible in room temperature. So whether I have to take it to high temperature and do it, not possible. Whether I have to get into a very low temperature and do it, yes, possible. So should it be 2 degrees, 3 degrees? No, not possible. It should be 50 degree minus, yes, maybe, or maybe minus 100 also. Okay. So quantum computer doesn't work in room temperature. It means like you can't have a quantum computing like a laptop, but that is the situation now. Got it? Now you come back to a traditional computing architecture. For example, if you take any computing architecture which is based upon von Neumann architecture. So initially when IBM found out, like it was as big as the room. Got it? Then it has become so small that we can hold it in our hand. Our mobile phones are even more stronger in terms of processing units than our laptop most of the times. So we have brought it inside our palm. Got it? So now, same like that, research will come in such a way that they will have plans to do quantum computing maybe in a normal room temperature, but it's going to be very difficult. But if you take a shape size of a quantum computer now, it's as big as a room, maybe half of the room, and show you a picture of quantum computing. But it needs a very sophisticated environment to do any kind of calculations. Means very sophisticated environment. Okay, it's not easy. And other hand, it's quite expensive. Okay, so it can be millions of dollars. Yeah, possibly. Okay. So who owns computing that can do quantum computing? Okay. Only few companies, and India also have started quantum movement. UAE is also about to start, and they are already discussing on it. So you can see many universities coming out with electives already, courses on quantum computing, quantum artificial intelligence, all that stuff. Okay. Now, like with that equipment, what kind of computation I want to do? Okay. So for example, you take quantum sensing, quantum networking, quantum computing, quantum simulation, quantum cryptography. These are the five major research area in which quantum energy is being invested. People are working towards that. Okay, these are the five major area, and already it is not only in a theoretical stage. Already pilot projects have been started, and you can see like a lot of in things are happening in terms of quantum advancements. Okay, especially you take quantum sensing. Okay, so what is sensing? Can anyone say what is sensing? How many of you have worked in IoT? Okay, so when you are working in IoT, like you know what is sensing, am I right? Okay. So how accurate a sensing should be? Okay, well, if you take an IoT, what is an IoT? How it is different from other devices? Any devices which has an IP address and part of a system and which can do something automatically is called an IoT. Am I right? So, like that. Okay, so every device that you have should have an IP address. Okay. So sensing, what it will be sensing? So it might be sensing a heat, it might be sensing a weight, so it might be sensing a pressure, it can be sensing an air quality. So these are all sensors. Got it? So now for you have a sensor. So it has been activated. So now you have another place where decisions are being made from the input given by the sensors. Okay. So for example, imagine I want to know how many airports in US are polluted more than the level it should be. Okay, so what I can do, I need to keep sensors all over the airport, and I know what kind of sensors to keep. It can be all types of sensors that can sense carbon monoxide or any elements in air or some particular thing, minerals in air that is not good for human. I can just keep sensors to understand it. I have chemical sensors which can immediately find out everything. Okay, got it. So I just put on a chemical sensor, a drop of blood. It can give complete report about the blood immediately within seconds. Like that kind of development we have. We have got nano sensors, which when we can paint it on the wall, it can show the temperature of the wall, the how it is. Okay, got it. Something like that. Okay, so now the accuracy depends. Imagine I'm going to make use of a sensor in order to understand somebody's heart pulse or blood pressure, and I want to say, like, dude, you might be getting heart attack in 1 week or 2 weeks, or there is a block and this block is going to completely block, which is not going to allow blood to enter into your heart, and so there is not a good probability of things to happen. Okay, if I want to say something like that, imagine how accurate my sensing should be. It should be very very accurate, because I'm going to deal with human life, and I'm going to deal with accurate, and I'm going to deal with critical systems. Okay, so then what I have to do, my activators and sensors should be better. Okay, so when I use quantum computing and quantum sensing, the accuracy is going to be very, very large. I'm just not talking only theoretically, but the quantum computing is going to take it in a bigger area. Got it? So we will have sensors which are so accurate that the accuracy will be 99 point something. Okay, more than that. But since that are in a theoretical state certain things, but certain pilot projects have been implemented in labs of in certain Harvard and Stanford. We'll go to that part also, but sensing will be much better. Okay, got it. Simple. So sensing and automobile, I can talk about it 2 hours. Got it. Sensing is one of the important thing that is needed for three things that are advanced topics. For example, autonomous vehicles. Second one is unmanned aerial vehicles. Okay. Third one is driverless car. There is a difference between unmanned vehicle, driverless car, and unmanned aerial vehicles. These are very different. Okay. So it has a smaller difference between three of them. But in all these three, the sensing is something that is very, very important, because imagine suddenly a cat jumps into the car. Okay. So how the braking should be done? Got it? Suddenly a bird is coming and falling into the car. So what should be done? This all are ready. The algorithms are ready. The inference theories are ready. We are using artificial intelligence to take quicker decision. But still, what about sensing? Whether it can be able to find out whether it's a bird or like some other cat or something else, a small piece of something hitting upon the car. Okay, we can't find that level of sensing is not there. But when we get into the quantum sensing, the sensors will be much better, and that is going to help us. Got it? So before we see quantum networking, quantum cryptography, simulation, we'll further get into the topic and we'll come back to the slide again. Got it? So these are the early ideas that has come, and you just note the year in which it has come. For example, 1979, 1981, 1980. Most of you would not have born. Got it? So imagine they have written about computer as a physical system in 1979. The microscopic quantum mechanical Hamiltonian model of computers, and they have represented using something called Turing machine. Everybody knows about Turing machine. Got it? So, and if you're keen, I'll be also giving you this PPT, but if you're keen, you can just go to internet and you can even download this and study. So they have completely like constructed a quantum mission and by means of Turing machines. Excuse me. So then you can see another article that talks about simulating physics with computing. Got it? So you can see it has been written by Caltech. Okay, so California Institute of Technology, it's one of the number one private university in US. They are completely into robotics, completely into AI, now also into quantum. Got it? When time permits, you can find out. And there is an article by a Russian, what are computable, what are non-uncomputable. Excuse me. So these are something that started people thinking into high performance computing, especially the quantum level. Okay. You can see these are certain algorithms that are there. For example, algorithm for quantum computing. Then you can see okay. Can you see the screen? Okay. Just a second. Yes. Got it? So you can see the algorithms. So what are the algorithms that can be done by means of quantum computing? If you take any of the cryptographic algorithms, for example, like inside cryptography, for example, you just keep a fingerprint. You go to a place, you keep a fingerprint, immediately door opens. Okay, so this is a simple thing. Okay, so what happens when you keep a fingerprint? Okay, it takes the data from your fingerprints and does a lot of permutation combination. It does a lot of factoring. Okay, so and it sends an encrypted data to a server or to the machine. Then it gives back, okay, this is an authentic, it is a registered fingerprint, allow or don't allow. Okay, so this is what we are getting. Am I right? Okay, so if you take this kind of algorithm, there is something called factoring. Okay, so which is a finite part of encryption decryption. So this factoring can be done very fast. So by means of quantum. And these papers that have been published long back, we were seeing about papers that have been published in 1979, 81 and all. So you can see these papers have been published in 1994, 96 and 2001. Okay. So these are certain fast quantum mechanical algorithm which can do so faster than the available computers available, and we have proven also. So you can say, Bala, I was talking a lot about quantum computing, but why it has not come? I told this going to take some time to come as it is not feasible to compute in a normal room temperature, plus it's kind of expensive. So now people are using it to find out only expensive problem for which the solutions are needed. Like one I told about understanding the brain, so for which they can use. So for example, if you want to do a Google search, should we do a quantum computing? No, not necessary, because the existing high performance computing itself is okay for it. So we don't use it for that kind of reasons. Okay. So you can ask me for what kind of reasons we should treat it. Okay. We have divided the problems that are available in the world into many types. Okay, got it? So let me see. Okay, these are the problems. Whatever problems you have in this world, this can be classified. Okay, so here we have described whether this problem can be solved easily. Yeah, it can be solved easily by means of computing, easy classifying. Okay, so what are this kind of things? For example, any search. Yeah, classical computing is okay. Traditional computing is much better. Any sorting? Yes, possible. Any clustering? Yes, possible. So any pattern recognition? Yes, I can do it. Okay. So any speed operation, yes, I can do it. So why quantum? Okay. Now there are certain things like which even quantum can't do. That is also there. But there are some things which is hard to be done using classical computing, but I'm going to do by means of quantum computing. Like that also, algorithms. For example, I was talking about like cryptographic algorithms. For example, factoring is one part of cryptographic algorithm, and I can do factoring when a super polynomial speed up. Okay, so whatever computing I'm doing, for example, I'm filling a form, entering something using an app, every computing has a measure which is called as complexity. Okay, so how long it takes for a computing to happen, so it can be order of 0, order of O, it can be NP hard, like that. Okay, so that determines how fast it is. So you can see here another diagram I have given. So what is the maximum time for executing the operations? All right. So when you say NP complete, it means it is non-probability complete. So okay, the operation will be completed within the time frame. So when you say NP hard, you are saying that it can't be done within the allocated time. It can't be done in a probable time. We do not know when it can be completed. Okay, so there are problems like that. Okay, so in order to solve that kind of problem is where we will be using quantum computing. Okay, okay, so these are the promises of quantum computation. So you can say, already I told, like we have more than bits, we have a lot of something called qubits. So here we can store exponentially information storage. Imagine, because data is not going to be stored only in 0 and 1, it can be stored by means of a methodology called entanglement, where one proton can store more number of data, and it is going to store it for a different time. When time t is equal to 0, this data, times t is equal to 1, this data, time t is equal to n, this data. So instead of taking two states, it's going to take multiple states, and for each of the multiple state, I'm going to get a data. So I can retrieve also. So what we are doing, though we have the silicon, like using it, we are going to retrieve it completely, and we are going to make use of it. So quantum computing, when it comes, imagine like is a small device. You can store like thousands of film movies. Okay, why I'm taking the example of movie is it consumes a lot of volume of data. Okay, got it. So once this kind of quantum computing storage comes, then one laptop you can just store all the movies that has come. Okay, so it is going to be in a different level of computational storage. Okay, by means of something called a concept called entanglement. Okay. Second one, there are a lot of problems. If you go to Wikipedia or if you go to internet, if you want to find out what are the problems that are already been solved, okay, what are the problems which has not been solved, you can get a list. Okay, there are a lot of problems which has never been solved, got it, in this world. Okay, so we have the list, and top scientists are working hard towards solving the problem. Okay, so what are the problems? Many things are there. So, and what will happen when we solve the problem? Okay, multiple innovations will come. Okay, got it. Simple. Let me say, we had only X-rays. Then we had scans, MRI scans, CT scans. So this is possible when they invented lasers, when they invented light, how a light can pass through a body, when they invented something around reflection, refraction, all that. But what are the applications of it? They invented new concept, but we are using the devices in order to even understand human body without cutting the body. Imagine CT scan is trans uh, cross trans scan. It means like it is as equal to cutting a brain or body and opening it and seeing that kind of image we are getting. Okay, it is not possible. But now, if somebody wants to find out whether the brain has a tumor which can't be seen even with human eyes is there or not, then what I have to do? Before long time ago, they have to do a surgery to find out whether tumor is there or not. But now I need not to do any kind of opening of the head. Rather, by means of a scan, I can easily find out because the penetration of light of different kind of physical entity leads me this. Okay, so I can do enormous, what you can say, revolution in this kind of things. Second thing, okay, imagine the classical computing is like a train. Okay, so or a car, you imagine it's automobile. So using car, I can go to certain areas of a city and I can explore many things. I can do a lot of things. Okay, so this separate. Now imagine like quantum as a cruise. So you know cruise. So now I am going to areas where car can't go. Okay, an automobile can't go in water. Am I right? So it means like I'm not going to solve any problem using an automobile in a waterlogged place. Okay. So imagine automobile like high performance computing, like AI and all that stuff. And this is a cruise which is going into the terrain which can't be covered by high performance computing. Are you clear with this? Can I get a thumbs up or whatever you want to say? If you are clear with the concept, okay, got it. So we are getting into untitled terrain and where this normal system can't go. Okay, so what are they? Understanding certain thing, especially understanding nature. Once we understand nature, we'll be able to create a lot of innovations around it. That's what we are going to do. Okay, revolutionize cryptography. Okay, got it. So if somebody wants to find out somebody's password, which is a very poor password, it has not been kept according to the nomenclature, needed to keep a strong password, then what will happen? How many years it will take? Yeah, it is going to take years. But imagine that guy is having high performance computing, NVIDIA systems, GPU, all that stuff. Still, it is going to take long time for him to crack it. Maybe not also, but still, it is possible. Okay, how it is possible is by means of quantum cryptography. Okay, quantum networking, or by means of quantum power, all the algorithms that are existing now will be taken into side. It means like all the algorithms we have, including RS algorithm, blowfish algorithm, or any other algorithm we have, like will be compromised. That's the right word. It will be compromised. Means once quantum computing come into live action, already they have done research using the existing quantum computing and they have broken multiple very steady algorithms there. All right. So once quantum computing comes into the main field, all the algorithms that is existing will be gone. So what will happen? Is it good or bad? Yeah, it's going to be very good because we will be coming out with quantum cryptography, which is unbreakable algorithm. So the possibility of hacking, possibility of something else in terms of authentication, in terms of access control, in terms of digital signature will be much better. Okay. Why it is better? Because it's going to become stronger. So will it be staying for whole lifetime? No. There might be any more technology that can come that can be much better than quantum, and it will be able to even break in quantum algorithm. So that's the thing. Got it? So now newer algorithm will start to come. So older algorithm nobody will be using. So all your maybe OTP is the one that has been serving the purpose. Imagine there is no OTP, the number of infiltration is going to be very very high, especially in banking sector, financial sectors like that. Got it? So like that. Okay. So so what happens in a quantum computing is I'm going to the finite level and I'm going to take how much of amount of thing it has been stored in proton, all that stuff, and how it is being totally isolated from the existing system, all that I'm going to see. Okay. So in order to control this proton, neutron, and electron, I have to get into a sophisticated lab and I have to watch it, and the data can be stored on it and it can be taken into account in a different way. Okay. So like what is the data, how it will be inside. Okay. So now the movement of atom has to be in such a way that it should be very calm, quiet, and it should be, we call it as a clean room environment, like for example, clean room environment is something like you can search which are needed for in an industry which manufactures even mobile, or clean room is needed for many sophisticated processing to happen. Okay. So here we need that kind of a totally isolated but very strong kind of place where there is no decoherence, where noise. Okay, I just for example take this water bottle. I just do something like this. Okay. So there is a water or there is a glass. Glass is made up of what? It is made up of atom, and atom molecules, everything is there. There is a disturbance in the glass. Okay. So if I'm just putting it down and breaking it, absolutely it is broken. Atom has a different level of disturbance. But even if I do a small sound or I just knock on it, still there is something happening inside in atomic level. Okay, so we have got microscopes to see it. Quantum computing also deals with what happens when I do something to the qubits which are stored as a part of atoms. That's what our challenge is, and people are working towards it. Okay, got it. So quantum computing is already popular in press. You would have seen it because anything that is going to give us speed will always be the best. Okay, that too high computing with speed. Imagine if I want to explore black hole, if I want to explore astronomy, if I want to explore astrology, if I want to find out petrol in a place which is deeply buried, if I want to find out natural resources in some space, if I want to find out people living other than a planet like Earth, these are massive problems. Got it? So, which is very hard for in classical computing to like find out, because there is issue with speed, there is issue with space. When only for this kind of problem. Normally, otherwise, the best is high performance computing. Okay, got it. So like, so these are the building blocks of quantum computing. One is qubits, another one is quantum gates, another is quantum circuits. Got it? So if you take a traditional computing, you have bits, you have bytes, you have circuits. What are the circuits we have? Or circuit, and circuit, not circuit, NAND circuit. Like similarly, why it is being used for doing some operations by the bits. Okay, so it can do gate, and gate, or gate. It can add, subtract, and then only we can do multiple things. Got it? So these are certain quantum algorithms that are available over internet also. I want you to note it down. Okay. So like there is something called quantum algorithm zoo, where multiple algorithms are being pasted, and it's very hard to create a new quantum algorithm, but you can still work in something like a quantum simulation environment. For example, we have something called Qiskit, 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 which is part of IBM, and um, you will be able to use that simulation. Once it is okay with operation simulation, then we'll be able to really implement it. Okay, got it? So like this algorithm here, what we have written is factoring algorithm. So factoring, as I already told, it deals with prime factorization, and this algorithm has an order of O of n squared times. Got it? So like now there are another algorithm which is a district log algorithm, and it is working in a super polynomial speed. Okay, these all are happening by means of the understanding of quantum environment and algorithms working on top of the quantum environment. I think so far so clear. Okay. Okay. So we will get exponential speed up, pattern recognition, Fourier analysis, efficient searches, minima finding and maxima finding, matrix mathematics. It can be used in linear algebra or machine learning, all that stuff. Got it? So what are the challenges of this? Okay, the qubits is very short time. Okay, so I just imagine I'm storing a qubits in water. It will not be there permanently. But when I shake, something happens to the atom, and the time span is very, very small. So I have to understand, I have to take the data and understand that qubit within that time frame. Got it? And noise. Noise need not to be a sound noise, can be a vibration, it can be pressure, whatever that distract and disturb the system. For example, if you have a quantum computer in a lab, if somebody is walking towards it, its behavior changes because it's been installed somewhere. Got it? So they have preparations, like they have arrangements in such a way nothing disturb the system as such. Got it? And we also have challenges in error correction. Okay, take a classical computing, like error correction code you have. It is very, very easy. You don't get much of errors, but here it's going to be very difficult. Got it? So I'm giving some examples of quantum. For example, we have Fourier transform, but there is also quantum Fourier transform. You can, when you get time, you can just go through it. I don't want to get into it because the crowd will not be able to handle it, because it's a kind of hardcore topic. But all this can be done by means of quantum computing. Okay, so let us go for Google. Please just look at my screen. I'm going for something called Quiskit. Got it? So anybody can install Quiskit, and you can write program using Python. I think most of your favorite language will be Python only. Can you see the screen? Can I get some thumbs up to understand? So you can build algorithms, you can do quantum research, and you can install it. Got it? And here you can see the parts of Qiskit. Got it? So you can use this Qiskit, and as I told, you can use Python to code. If you want other languages, also you can use. And we have also a repository for that. You can see it, and it has been put in GitHub format. Okay, so what you can do with this? You can build quantum gates. As I already told, we have something called quantum bits, bytes, and then circuits, all this stuff. And you have got tutorials if you want to learn about this. For example, let me take a tutorial. Got it? How can sample-based quantum diagonalization of chemistry Hamiltonian can happen? Okay, got it. So like you got this circuit. Okay, so this method. So you can do a lot about it. Got it. So now I'm going to, so because taking taking just lecture is very easy, but when you want to like quantum simulator online, got it? So there is a simulator called Frick. So it's a very good simulator. Got it? Can you see this? Okay, I can edit a circuit. So you can see like and create. So this is going to be a little hard for people who are starting with. But whatever is hard, that's what you have to do. That will make you different from other people. Okay, got it. So I can create my own gates. Okay, let me check. So how to create gates for an quantum algorithm. Okay, you got it. So you can find out the logic gates. Now I'm coming here. So I can just on it or off it. I can take something and use it. Okay, I can create anything. Imagine I'm going to create an algorithm for cryptography. That algorithm might be needing spinning, some formula, some parameters, some sampling, some input, some output, some frequency, some arithmetic. All these are all set up. Okay, you can see all these are all set up, and I can again make it better. For example, you can see for a series gate. So I can do it, and then I can make a gate. Got it? From matrix or from rotation or something. Got it? And then I can like export the gate to a JSON file. Got it? And I can run it. Okay, that is a possibility. I can do it. So I think hopefully this will be useful for you. So this is called as Quirk, Quirk. So when you just go it, like just study it, that will be very, very useful. Okay. So similarly, this is a gate that has been created by one such software, like for example, Qiskit, where we can easily build this kind of softwares. Okay. So now, for example, if you take, if you given an integer P and Q for primes and determine, so best classical algorithm is also there. Okay, got it. So we can find out why we are doing the circuit. I'm doing an algorithm. With classical computer, it's going to take this many seconds. With quantum computing, how many seconds it will take? That's what I'm going to find. Simple as that. Got it? There is something called Shor algorithm that is very hard to implement, but once this is implemented, it will be completely reducing the uh, what you can say amount of time because it reduces the factorization point. Okay, so this will help us. Why we are doing this? This will help us to identify or to identify the problem in a better way and to solve the problem in much better way. Okay. Then we have called as Grover's algorithm. When you think about Grover's, it's search algorithm. Got it? So unsorted databases. and uniform superposition of all over possible solutions. So imagine classical computing is going to take order of n, but Grover algorithm is going to take only order of square root of n. It means its failure rate is zero. Is going to take very less time than what we really take. Okay, imagine like search is so fast. Okay, so you take a database of like a country like most populous country, their citizens database. Now, if I want to search certain like what you can say, certain attributes inside, it's going to be very difficult. Or if I'm going to take identify some materials that can be partially radioactive, because radioactive materials are available only with particular countries. Unless they give the material in some milligrams, we will not be able to do anything out of a nuclear reactor, which many country has built. That cost multiple $1 million. But unless you have that uranium, titanium, or that metal, you can't run the nuclear power plant. Okay, so people are always, every government is investing a lot of money to understand what they have beneath their ground. Okay, is there any minerals available? And you can't just keep digging to find out, but there are a lot of artificial intelligence based or quantum AI based representing some analysis we can do and find out whether something is there or not. Even people are finding in newer petroleum in sea and all that stuff. Got it? So you can just see this kind of matrix can also be done by means of that. Okay. So these are certain things that are available for doing programming in quantum computing. Got it? So what is this programming? So we have Qiskit, we already saw. Then we have Crick, that is from Google. We have Ocean SDK, that's from D-Wave. And we have some Forest SDK, which is from Cure. Okay, so anybody of you can install it in your system, both online and offline, and you will be able to work on it. And as I already told, you can use program language like Python or C++ to code. So these are some simple like programs that have been done by means of Qiskit. So this is the program you are going to write, and this will be the outcome. So outcome, how it comes, it doesn't come in numbers or it doesn't come in words, but we have something like coming as a circuit. So that's what you understand by means of the simulation software. And if you really build a quantum computing and use this circuit, it will work. That kind of feasibility is only taken into account. Okay, quantum error correction, as we already told, it's going to be very, very hard to find out noise to correct, because even a small sound or small interference into the system will change the entire operations. Okay, so these are error correcting codes. Error correcting codes in quantum is more than normal processing. It takes a lot of time to other methods of error correction. You can see fault tolerant quantum computing, quantum simulation, anything like they have said nature is in classical, and if you want to make it a simulation of nature, you would better make a quantum mechanical. Okay, what do you mean by that? So nature is never a classical in the sense it's never forms the pattern of a classical computing. And if you want to simulate nature, how a tree works, I want to make an artificial tree, which has been done. You did make it quantum mechanical. It means unless you understand the logic how a tree works, quantum mechanical, you can't make it. Imagine people are creating artificial lungs, artificial hearts, transplantation is going, and everything is working fine, not big trouble. Okay, so when we hear something, if the technology is in trouble, then only we possibly understand. But it's not like that. Okay, well, so like these are certain molecules which are taken into account for doing this quantum computing, especially like you can see, instead of taking gold, they have taken beryllium hydroxide molecule. Now they are doing computing inside it. Okay, so your Qiskit will have the properties of this beryllium hydroxide molecule, and accordingly it will be like working. And then like you can see, one sec. Got it? So here you can see they have taken into account as a particular molecule, and that molecule is been trapped into an ion and they are measuring it. Got it? So like you can see, this can be done by means of simulation. So they will take all the properties of the molecule and do it. And every day people are inventing newer way of materials which can be used very easily for quantum computing, because nowadays currently they're using very expensive material, rare materials, but slowly, eventually, maybe in some years to come, they will be using quantum computing with normal minerals and materials only. So that is okay. Quantum advantage, okay, like dramatic speed increases, problems that can't be solved, it's going to be taking supremacy. Got it? So Nature also have published as paper. Got it? So they have done sampling of numbers from pseudo-random quantum circuit. So sampling of numbers is also not that easy. Okay, but imagine we have a large data set and I want to sample. It's going to be very hard, because creating a sample set is not easy. So this has been done by means of quantum advantage. Okay, they have done this. So far, so good. Is it good? Can I get some thumbs up? Okay. Uh, Miss Maya, how much time I have left?
So hopefully, how much slides do you have, sir?
Ma'am, I can complete in 15 to 20 minutes. Is it okay?
Oh, okay, sir. Okay, sir. Take your time, sir. No issues.
Okay, ma'am, perfect. Got it. So it keeps on going. Like you can see how we are doing sensing, how we are doing imaging, how we are doing this. Got it? So if you take this slide, you can see like these are certain simulation that has been done in this world. Got it? For example, you can see digital twin. Okay, got it. So what do you mean by digital twin? I'm going to simulate certain thing like this. If you take till 2000, if you want to make a rocket, they'll make a smaller rocket, how it works, the parts of it, and then they do the simulation. Okay. This has been done by means of 3D modeling, CAD CAM, remote programming, CNC, all that stuff. Okay, similar. So I will just make one model of it and another thing. So this kind of simulation was done. Okay. So now, secondly, after 2003 to 2014, people started using completely computing to understand something before they create. For example, you want to create a bike. You just don't go into mechanical area at all, but you will understand the complete working of bike, how it is, all that stuff. Got it? And then you draw it, you do the digital design, you do the virtual assembly, you do the simulation, and no physical commitment. And then we use 3D printing, then print it. Got it? So this kind of thing gave complete innovation, and newer products have been coming into the market every day. New product. People think it, and it is ready. For example, in during 2000, you didn't have much of products only in this world. Okay, but this kind of designs, this kind of digital twins made it much better. Okay, now after that, in 2014 to 16, we got complete connection between the virtual world and the physical world. Got it? So we call it as data unification. And here we came out with something called IoT, we came out with something called big data analytics and cloud. Got it? So you can see which is virtual, which is reality, or both are same. Okay, so I can get rapid feedback across all these designs, manufacturing and operations, and projects are augmented by means of digital services. Got it? So now what is happening is, by means of the quantum power, we are using holographics, we are using AR, VR, and completely you can design. You would have seen a lot of videos. you can have guided interactions. You can use AI, quantum computing, and all that stuff, and you can blend human computer interfaces and collaborations. Okay, good. So that's how autonomous and self healing, everything is happening. You can see this picture. Got it? So every system is in front of it, in front of you, and you will be able to experience it. And after experience it, you will be able to do some innovations into it. Got it? So digital twin means it's, what you can say is, it's a representation of a real world, but inside a monitor or inside an environment. It can be a small table on which AR VR is there, and you are doing some controls using it, and you are doing some experiment using it. Okay, got it. So now we are finding out how HPC and quantum computing are going to work together. Got it? So if we have certain future that is foreseeable, then it's the future of HPC, high performance computing, getting in action with quantum computing, QC. All right, so that's what the thing. So you can see a typical quantum computing architecture. So you can see this. You can see this complicated architecture, a lot of wires and this, that, because these are tubes in which certain molecules are moving, and these are converted into certain electricity or some understanding, and then we are doing this. Okay, and this kind of systems are kept in places like Alaska, or maybe undersea certain thing, and because they need to maintain certain completely noiseless, completely noise, or don't think only sound. Okay, it's multiple, even vibrations. Imagine you are building a physics lab, and you want to know about what you can say, crystal growth or something like that. So you can't keep in a floor where people are walking. That also will disturb the crystals and their growth. Correct. Similarly, this also, like you can see this, like top companies are having this kind of thing, sophisticated thing. Got it? So now you can see the scenario, like if you see the parameter of system, I can create a quantum state for the system. I can understand the energy of the system, and then I'll be able to optimize using this. Okay, so this is a combination of how classical computer can interact with quantum computer and get some output from quantum computer. Got it? So these are the specific things in which we can use all this. For example, we can use it in manufacturing, we can use it in automotive, we can use it in construction, we can use it in energy and utilities, we can use it in healthcare. Imagine healthcare. Got it? So if I'm talking about healthcare, the main thing what we have to talk about is like prediction of a disease. Imagine if somebody is having a disease and it has been predicted rightly that this guy is having this disease, then almost 50% of the disease is cured because I have predicted it rightly. But most of the time, the prediction is not done rightly. And what will happen? Because they have predicted a wrong disease, what they are going to do? They are going to give wrong medicines, and that medicine is not going to treat what they have, and it is going to deviate, and it's going to create new diseases and much more. And the rest is history. So similarly, if somebody coughs, what is the why they are coughing? We don't have technologies to understand the root cause analysis. But when HPC and quantum computing are tied up, we can easily find out technologies which are faster, which are more accurate, and all that stuff. Transportation. So unmanned aerial vehicles, we were talking about a lot of novelties. Imagine the top-notch Fortune 500 companies are completely investing their money on transportation. Like suddenly how we got an Apple product like an iPhone or a Shuffle. We'll be suddenly one day Apple will be releasing a new car. Imagine, I'm saying maybe in a 5 years, less than that, they'll be introducing a new car. So already we have been like given a new brand called automobile called Tesla, which is no a mechanical part, which is a completely electrical computing and all that part. Got it? Similarly, Apple will be releasing a new car which will be completely different from the way the other automobiles work. It will be very sophisticated. It will be another iPhone. I'm very sure about it because they have been doing this research for 15 years more than that. But unless they do really path breaking research, they will not be giving it. And they are okay to wait because they want here, for example, if you take all the Apple products sells 3 to 4 times the cost of normal product, but still people like it and buy it, and they don't have competition. And every year during the September, October, they go for a release, September, and still they increases. Okay. Construction, the way we construct, it can be improved. Energies, always energies, identifying energies, newer energies, the utilities of that, sustainability, all that is coming up. And even retail, sports, all this digital twins will work. Inside quantum computing, so what is that I should read? If somebody asks, Bala, what I should read? You concentrate more on quantum sensors because it's going to be upcoming. These are the trends of 2025. And then you concentrate on hybrid quantum applications. For hybrid means it's not pure because pure quantum applications are expensive. So it's a combination of HPC and quantum computing. Quantum communications, novel qubits, advanced materials, post-quantum cryptography, quantum simulations, fault tolerance computing, cloud computing, and quantum machine learning. Imagine quantum machine learning will be really, really powerful. And we have done some books on that kind of quantum machine learning also. So these are the trends that you can concentrate. Got it? So, like, is it possible, feasible for us to connect high performance computing, quantum computing? Yes, it is possible, it is feasible, and it is further ado, we can do a lot of things. Got it? So, like, where it should be added and how it should be added, that's a big challenge. But we have already got frameworks which integrates all this. You can see like characterizing quantum computing hardware to suppress errors or mitigating measurements. All this is being done now. Got it? These are certain publications we did. Okay, so basically we did long time ago, maybe 3 4 years back, and here also we did something on quantum networking where we understood quantum channel optimization. So this is a very important theory. Like, for example, we get traffic when we during communication. Communication is very expensive and the accuracy is not great. Okay, so but when quantum channel optimization has happened, the completely it is a very different strategy and it is completely inspired from machine learning technologies. So another book we did, quantum blockchain. So making the security more powerful, completely unbreakable kind of thing. So imagine we have even written a chapter in which we talked about a small chip that can be put inside a human hand or any part and it can store all the data. So you just get into your friend's computer, you touch his computer, and all the small data is being absorbed by small chip, and you go to your system, touch it, and it get all transferred. Got it? So such kind of intelligence are there. So we can use it for GPS satellites, we can use it for medical imaging, geological surveys, nuclear monitoring, medical applications, accelerometer, gyroscopes, all can be used. Okay, so this is the promise of quantum computing when it is combined with like artificial intelligence and quantum processing units already exist. Like we have now we use GPU, graphical processing unit. Now quantum processing unit is there. What I'm talking is not frictionless. It's already there. For example, if you want, you can get into this lab. There is this lab. I will show you this. So this computing facility is already available. If somebody wants to go and do some research as a student for internship, you still can apply. Okay, so it's a complete uh, computing lab. They have certain programs also where they do simulations, they create a lot of applications and all this stuff. So you can see what kind of computing resources they have in order to understand. So system resources, IBM Quantum, everywhere IBM is leading the way for now. So they have all this quantinum. You can see this. So it can be used, and most of the developing countries like US, Europe, Japan, Australia, Canada, China, Russia are investing significant amount in quantum research. So you can see a combination of HPC and QC. So you can see quantum computing user program. Anybody can be a user here and you will be able to understand how this quantum computing work and enable your research. That is also possible. So this is a page completely for that. Oak Ridge National Laboratory and how these things can happen, all this stuff. So newer devices are being done. I've told about this. So for example, if you need to understand a protein structure prediction, imagine if a child, once it is born, I'm taking a protein out of the child and I'm doing analysis, collecting the data. Now I can easily say this child, when it is 15 years old, she is going to get this disease. This child, when she is going to get 50 years old, she might be getting heart disease. So once I can understand that very early prediction, then I'll be able to give her a lifestyle, give her a space that, see, this is your condition, you have to live like that. This kind of predictions can be done by means of quantum computing because normal computer is not equipped. When a disease come only you can detect or you can predetermine little bit before, but not dynamically. That's where quantum dynamical simulation is going to work. Quantum chemistry, quantum error correction, all will be working. Got it? So that's all from my side. So it's pleasure talking to you people. So if you have any further queries, you'll be able to ask me. I'll be able to answer it. Thank you.
Thank you for that enlightening presentation, Doctor. We will now open the floor for any questions. If you have a question, please type it in the chat box. Alternatively, you can feel free to open your mics and ask questions. We kindly request you to keep your questions short and brief so we can accommodate as many as possible. And also, we will be sharing a feedback link in the chat, so if you could please fill that out, it would be really appreciated. Over to you, sir.
If you have any questions, you can ask. There is a question whether QC, that is good, you are using the word QC, will mitigate the cyber crimes or complete eradication of cyber hackers. Yeah, there is a possibility because we are going to strengthen the algorithm. Once we strengthen the algorithm, it's going to be much better. We will have stronger algorithm, but we will not be able to always eradicate cyber hackers because when we are working hard to create encryption, decryption algorithm, they are also working hard to break it. Okay, so when we are understanding by means of crypt analysts working on how good this algorithm is. Other hand, multiple people are also working on it, but can't be eradicated. But still, like you said, it will be eradicating many of the cyber crimes to a larger extent. Now also you can see more. For the last 2 to 3 years, cyber crimes are not an increase because we have really strong algorithm, hardware based algorithm, software based algorithm, expert finance. Imagine everything is online now. If one such things happens, It is very brutal. There is a possibility a cybercrime can completely derail the economy of a country. So that's the thing. Any other questions? I think you people got a glance of what I said, and it's something very new, like that you will not be able to ask much of doubts. But anyway, thank you very much. Thank you, Professor Pan. And thank you, Maya. Thank you, Dude, for and just giving me this opportunity. Thank you very much.
Thank you, sir. Kindly stay on the line.
Sure, sure.
We'll introduce about FEDA to all members.
Okay, perfect.
Sahal, over to you.
Thank you all for your engaging questions, and thank you once again, sir, for the insightful responses. To formally close today's session, we would like to invite Dr. Meena Kumar from the FEDA Global Council to deliver a vote of thanks.
Hello, Dr. Balamurugan, sir.
Hello.
Good evening, and good evening to all the participants. Thank you for the opportunity. Actually, when we saw your profile, we were all excited, like top 2% Stanford scientists. So I had invited all my team members in the organization to join in, so that what is the basics of QC can be understood and how it has been utilized in the daily life. Though it is a bit out of the work, maybe they will understand there is a world existing outside where all these improvements are happening. So that was the intention of joining in. Because physics always, we had a thought process that it is way beyond our control. But the way you have explained to us that how it is being utilized in daily life and how it is having impact in healthcare and all the other industries has given us an input that how we are benefiting out of physics and the science innovations which are happening across the world. Thank you so much, sir. And about FEDA, Federation of Economic Development and Association, is part of the central government where we are supporting the businesses across the world. And currently in the Global Council, we have around 7-country membership. And we invite all of them to connect with us and as well as benefit out of the global connections we have and enhance their entrepreneurship across nations. So, keeping it short and sweet, we are actively supporting all the current economic, trade, and investment affairs of the governments in India, UAE, Canada, China, USA, and UK. And we are progressing towards multiple countries. And using such forums, even students, entrepreneurs, businesses can flourish. So that's a short introduction about FEDA. The coordinates will be given for connecting with us. Please do make use of it and let us grow together. Thank you so much.
Thank you, madam, for the wonderful speech.
Thank you very
Thank
much.
you.
Thank you very much, Miss.
Thank you.
Thank you.
Thank you, sir. Thank you so much. Thank you for all the participants who joined. If you want to join in FEDA, I will share you the invite link and everything to each and every individual, and as well as in the group. I will coordinate accordingly as an individual or as a corporate. So thank you so much for this wonderful section, sir.
Thank you.
Thank you for everyone who had participated. So kindly share back your feedback to the group. We had shared the link. Thank you, sir.
Thank you so much.